Hello everyone. I'll be talking about fast secure computation for small population over the internet. I'll first give a quick run of our results and then go into the details. So the objective is to attain efficient constructions of three-party and four-party protocols secure against one corruption and achieving stronger security notions of fairness and guaranteed output delivery with a minimal overhead compared to the most relevant state of the art, which achieves only selective abort. More concretely, in the three-party setting, we achieve a 4-round fair protocol and a 5-round GOD protocol. And in the four-party setting, we achieve guaranteed output delivery and provide two variants of protocols, one with 4 rounds and another with 5 rounds. We achieve all these results with the assumptions of one-way permutations or one-way functions and with a minimalistic network of pairwise point-to-point channels. Only for a result of three-party computation that achieves guaranteed output delivery, we assume a necessary broadcast channel owing to the result of Cohen and others in 2016. Now with this, let's begin with a quick brush up of the definition of secure multi-party computation. Let us consider a set of parties who wish to compute a joint function f on their private inputs x1, x2, and so on. If these parties could trust an external third party, then the computation would be pretty simple. They could simply give their inputs and get back the output. But real world has adversarial parties and trust issues, which is why MPC has evolved over the years to tackle this problem of secure computation while guaranteeing the goals of correctness of computation and privacy of inputs. In other words, we can say that MPC is a real-world emulator of a trusted third party. Now let us quickly motivate why MPC with small population and honest majority is interesting. Although the traditional MPC has focused on arbitrary number of parties, recent studies indicate that there's vested interest in three-party and four-party computation, mainly because the plethora of real-world applications these settings have to offer, such as the first large-scale deployment of the Danish sugar beet auction or the secure ML applications like we saw yesterday, and many others. Also, having honest majority allows us to have weaker assumptions and eliminate expensive public key primitives such as oblivious transfer altogether. Also, the small party setting allows us to use lightweight and customized tools, and as a result, the resulting constructions will be extremely efficient. For instance, we could use customized secret sharing tools such as replicate secret sharing or customized OT primitives, unlike the traditional ones which use public key primitives. Also, an important point is that if you have honest majority, then the stronger security notions of fairness and guaranteed output delivery can be always ensured. So these are few interesting things that allow us to gain efficiency in the small party setting. Now, I will introduce you to a few security guarantees that will be used throughout the talk. The first is the strongest notion of security called the guaranteed output delivery. In this setting, no matter what the adversary does, the honest parties always get their output. A slightly weaker notion of security is that of fairness, where if the adversary gets the output, then so do the honest parties, else nobody gets the output. Another important security notion that is widely explored is that of security with selective abort. In this setting, the adversary can get the output for himself and then strategically behave in a manner and deprive honest parties of output, or he may deprive everyone of the output. So the arrow mark indicates the implication from the strongest security notion to the weakest security notion. So I'll be talking about the first two security notions in this talk. Now I will introduce a primitive called Garbled Circuit that is crucial for our constructions. Consider a Boolean circuit C with an input X and an output Y. Now, the procedure for Garbled Circuit goes as follows. The Boolean circuit C is transformed with the help of a garbling function into an encoded circuit called the Garbled Circuit. The garbling function also outputs the encoding information E and the decoding information D, which are exhaustive mappings of the all input and the output wires. Now, the actual input X and the encoding information E are fed to an encoding function to get the garbled form of the input. Now the garbled circuit is evaluated on this garbled input with the help of an evaluation function to get the encoded output. Finally, the decoding function maps the encoded output back to the original output with the help of decoding information. Traditionally, the construction of garbled circuit is handled by one party and the evaluation is handled by another party. With this idea, let us now view a bigger picture of our protocols in the small party domain. We start with the three-party protocols. The current state of the art at the time of the paper was that of Mohasel et al., which achieved selective abort security in 3 rounds in an extremely efficient manner with the use of only one garbled circuit. Now, the number of garbled circuit used is crucial here because the bulk of the computation and communication is constituted by the garbled circuits. Also, the protocol of Ishai et al. In 2015 achieved selective abort in 2 rounds, but they required 3 garbled circuits. The recent crypto paper of Patra et al. Achieves the security notions of fairness and guaranteed output delivery in optimal round complexity, but they require a minimum of 3 garbled circuits. In this paper, we start with the protocol of Mohasel et al. And achieve fairness in 4 rounds and guaranteed output delivery in at most 5 rounds, maintaining the number of garbled circuits required to be 1. So we also have a necessary broadcast assumption for our guaranteed output delivery protocol, and the same is reflected in the paper of Patra et al. As well. Now, if we relax the number of parties to 4 while maintaining the optimal threshold, we can have 4-party protocols which do not require broadcast. So the state of the art, Ishai et al. Achieves guaranteed output delivery in 2 rounds, but with an overhead of 12 garbled circuits. In this direction, we improve on the efficiency and obtain a 4-round guaranteed output delivery protocol with the use of just 2 garbled circuits and keeping all other constraints to be the same as that of Ishai et al. We also show that if we increase the number of rounds by 1, that is the total round complexity to be 5, then we can achieve guaranteed output delivery with the use of just 1 garbled circuit. Now, with the knowledge of all this comparison, I will now talk about our 3-party protocol with fairness, which is the simplest protocol of our lot. We first begin with the protocol of Mohasel et al. And then cite the challenges that occur in achieve fairness and then address them. Let's consider a set of 3 parties, P1, P2, and P3, with the inputs x1, x2, and x3 who wish to compute a function f tolerating at most 1 corruption. Now, unlike the traditional way, we allow 2 parties, P1 and P2, to enact the role of a garbler and P3 to act as an evaluator. P1 and P2 share a randomness R required to construct the same garbled circuit, and at the same time, P3 would secret share his input among the 2 garblers while preserving privacy. Having done this, now both the garblers use the randomness R that is shared to generate the garbled circuit, and this garbled circuit contains some information that is common to both P1 and P2, such as the garbled circuit itself or the decoding information, etc. Such common information is communicated by both the parties and is same, and P3 can simply verify the correctness of this common information by comparing the copies sent by P1 and P2. Since there can be at most 1 corruption, this suffices for the verification. Also, the private information includes the garbled inputs itself, which are individually communicated by P1 and P2. Finally, if P3 is happy with all these checks, P3 would then proceed to evaluate the garbled circuit to obtain the encoded output Y and eventually decode it to obtain the actual output. But P3 sends the encoded output Y to both P1 and P2 to help them reconstruct the output, since P3 cannot forge an encoded output without being caught. Now, this summarizes the protocol of Mohasel et al. Now, where does the violation of fairness occur? So let us consider a corrupt P3 who, on obtaining the encoded output and subsequently the actual output, might decide not to send the encoded output to one of the parties, or might decide not to send to both the parties. In these situations, fairness is violated as the honest parties don't get the output and the adversary does. So what are the possible solutions with which we can fix this? One thing that we could do is to prevent P3 from getting his hands on the decoding information until he communicates a valid encoded output. But we also need to take care that the decoding information is committed by the gobblers in advance, because one of the corrupt gobblers might later reveal an incorrect decoding information. Having done this, another important strategy is that we allow P1 and P2 to exchange the encoded outputs to prevent P3 from selectively sending to only one of the parties. And also, P1 and P2 exchange the encoded output only if they are satisfied with the validity of the encoded output sent by P3. Now let's see if these solutions fix all the problems and guarantee fairness. Now, a corrupt P3 on evaluation might decide to send inconsistent Y to both the parties P1 and P2. Now they check for the validity of the encoded output, and for P1 it does not match, and for P2 the check goes through. So P1 does nothing and simply waits for P2 to send something. For P2, since the verification has passed through, P2 would send the encoded output Y to P1 and at the same time allow P3 to construct the output by giving him the decoding information. Now both P1 and P3 use the information sent by P2 to compute their outputs. Seems like everything is fine and everybody was able to compute the output. But how far are we from fairness? We're almost there, except for the following hurdle. Now let us consider an honest P3. And an honest P3, after receiving the common information of the garbled circuits, concluded that the correctness check failed, and that's why he aborted the computation. Now, P3 would not send any encoded output to both P1 and P2. If P1 is honest, then for him this case is indistinguishable from the case when P3 was actually corrupt and did not send him any encoded output. So if P2 is corrupt, he can take advantage of this situation and cook up some valid Y because he knows the entire randomness of the garbled circuit and send the same to P1. Now P1 would simply perform the validity check and it would pass, and as a result P1 would accept this as the output. But we can see that correctness is violated in this case, which is a major setback for achieving fairness. So what could be the solution? One solution could be that we need a proof mechanism to allow P1 to be certain that whatever the encoded output he received from his co-gobbler indeed originated from P3. Now let's quickly look at the proof mechanism. So the intuition for this proof mechanism is that, so let's say the gobbler P1 shares some private data with the evaluator P3. Later, when P3 performs evaluation, he will send the encoded output along with this private data to P2. Now, if at all P2 is sending the encoded output to P1 to let him construct the output, then he will also send this private data to convince P1 that the encoded output indeed originated from P3. So procedurally, let's see how this happens. So P1 and P2 both sample a random S1 and S2 and compute a pre-image resistant hash values on it. So they send the same to P3 individually, and at the same time, they also exchange the hash values among themselves. Finally, they would also send the hash values received from the co-gobbler to P3. P3 would then perform checks to verify whether all the hash values and the corresponding pre-images match. Now, this is done before evaluation. Now, if all these checks pass through, P3 would then go on evaluating. After evaluation, P3 would send the encoded output and S2 to P1 and the encoded output and S1 to P2. Now, if at all, P2 verifies that both the encoded output and the proof that P3 sent is valid, then both P1 and P2 would exchange the encoded output and the corresponding proof values. Now, if an honest P1 is accepting the output from P2, then he can just verify for the validity of the proof that P2 sent, and if he's satisfied with it, then he's certain that P3 indeed sent the encoded output. So having addressed all these cases, now we can say that fairness is guaranteed. So let's quickly summarize what we saw till now. So in the first round, P1 and P2 would share the randomness, and at the same time, P3 would split his inputs among the two garblers. Also, the setup for the proof mechanism is done in the first round. And in the second round, the parties P1 and P2 would send the garbled circuit information and the hash values to P3. Now, if P3 is happy with all the checks, then he proceeds further for evaluation in round 3. In round 3, P3 on evaluating would send the encoded output and the relevant pre-images as proofs to both the garblers. Now, the garblers will individually verify whether the information that they received from P3 was indeed valid, and if so, then they forward the decoding information to P3. And at the same time, they also exchange the encoded output and the relevant proofs to help each other construct the output. Now, this completes fairness. Let's see what are the possible challenges that could occur in achieving guaranteed output delivery. So in the previous protocol, we saw that whenever P3 found conflicting messages from P1 and P2, he could simply abort, and that was okay for fairness. But in guaranteed output delivery, we always need to find a way to proceed with the computation since we need to obtain output in every case. So following would be the major challenges. So what should we do if we see conflicting messages sent by two parties during the protocol execution? Also, if one party locally identifies another party to be corrupt, how do we proceed? We also need to ensure that an output is computed only on a unique set of inputs and that the adversary does not get outputs on multiple inputs. So in the three-party setting, we resolve these challenges by allowing parties to raise conflicts with the help of broadcast and thereby resolve them. In light of raising conflicts, we also have a mechanism to identify an honest party and use him as TTP to construct the output. We address the challenge of input consistency with the help of commitments. In the four-party setting, the achievement of guaranteed output delivery is slightly more challenging, and we explore the setting of multiple garblers and evaluators, how to guarantee that there always exists one honest evaluator. However, this also gives rise to problems such as we need to ensure that both garblers send the same data to both evaluators, and also that one evaluator should be certain that he got the correct garbled inputs corresponding to his co-evaluator's input. In the worst case, we also allow parties to raise conflicts and identify an honest party as a TTP. Similar to our three-party computation, we allow commitments to enforce the input consistency. Now, having said this, now let's look at the efficiency of our protocols and the overhead in comparison to the most relevant state-of-the-art of that of Mohasil et al. So the table indicates the values of average per party, and also the range is taken over the choice of the circuits, and we have averaged it out. So in the three-party protocol that achieves fairness, we can see that the overhead of communication is very minimal and amounts to about 8 kb. The increase in the network time in the WAN setting indicates the fact that we have one extra round. And in the four-party guaranteed output delivery protocol, we actually gain in terms of per-party computation and communication. This comes from the fact that our protocol is asymmetric and we allow one party to be almost idle except for the input sharing purposes and getting the output. Also, in the three-party guaranteed output delivery protocol, we can see that the extra communication is extremely minimal and amounts to about just 0.4 kb. And however, we can see that the LAN computation is slightly more due to the fact that we use a robust broadcast channel. However, we have not implemented a robust broadcast channel for the WAN setting, and as a result, we do not provide the values for it. Finally, I will conclude with few open questions. An interesting open question would be to minimize the number of rounds of interaction while maintaining the same efficiency as ours and achieve fairness and guaranteed output delivery in the three-party setting and guaranteed output delivery in the four-party setting, thus bridging the gap between the optimal round complexity and the efficient round complexity. So that's it. Thank you.
Time for questions. If anyone has any questions, please come up to my microphone.
Hello. It looks like you are using an assumption that the honest party will not collude. How can you justify this assumption?
So you mean to say that the
honest parties, you are assuming that the honest party won't collude with each other.
Yeah, so that is the setting of the secure multi-party computation.
No, that's not. For honest majority, we can still assume that the honest party may collude with each other.
So in the real world, you're saying that the honest parties are always semi-honest?
Yeah, they're always semi-honest.
Yeah, but according to the definitions of secure multi-party computation, we can always assume that
no, that's not the case. Thank you. I always.
Any other questions? Okay, so let's thank the speaker again.